Welcome everyone, my name is Mirko Köhler. I'm from the Technical University of Darmstadt and I'm going to present to you today our paper Rethinking Safe Consistency in Distributed Object-Oriented Programming. This work has been joint work with my colleagues Nafise Eskandani and Pascal Weisenburger, as well as Alessandro Margara from the Politecnico di Milano and Guido Salvaneschi from the University of St. Gallen. So in the title we are using the word consistency. So let me start with explaining to you what we mean by that. Assume we have some data and multiple clients from all over the world. Having the data only in one place has the disadvantage that clients that want to access it that are far away may have a really high latency. Other disadvantages could be that we lack scalability and fault tolerance. Instead, what we can do is we can replicate the data on multiple machines. Amongst others, this is the advantage that clients have reduced latency when the data is placed nearer to them. However, now we have the problem that when we change the data in one place, then the other replicas have to be notified somehow. In general, we need some kind of coordination for that. And coordination can decrease the efficiency and the availability of the system. So for example, if we require to immediately notify all other replicas of a change, and one of the other replicas is offline, then we have to wait until this replica comes back online in order to perform the change. And this affects availability. If we do not require immediate coordination, however, then we can perform the change and notify the other replicas at a later point of time. This, however, leads to temporarily inconsistent replicas, which could then lead to possible wrong application behavior. So we have a trade-off. We can, on one hand, keep the replicas consistent, or on the other hand, have availability. And if you look at some real-life databases, we can see this conflict. So for example, Cassandra allows programmers to define a consistency level per operation, which states whether you want to have a strong consistency for an operation or you are fine with high availability. REAC, normally a data store that only supports eventual consistency, which is a weak consistency level, has experimental features to add stronger consistency models. And in MongoDB, reads and writes can also have a specified consistency level, for example, linearizable. So these were just 3 examples. However, there are many consistency definitions, as shown in this graphic from Viotti and Vukolich from the year 2016. So now the question arises, what is the correct consistency level to choose for my application? On one hand, we have strong consistency, which reduces programming complexity. So for example, sequential consistency reduces programming complexity by disallowing concurrent operations. However, such levels require immediate coordination between replicas, as the replicas have to synchronize to decide an operation order. This immediate coordination reduces availability. On the other hand, there are weak consistency levels, which require the programmer to handle concurrent operation, which increases the programming complexity. These consistency levels do not require immediate coordination and thus have a high availability. Eventual consistency is an example of a weak consistency level. So normally, applications require different consistency levels for different functionalities. So for example, payments may need strong consistency, whereas instant messaging can only use weak consistency. Now, when we have such an application, why can't we just use both consistency levels when we need them? So we can get efficiency where possible and correctness where needed. One problem with that is that mixing consistency levels can lead to violating guarantees of strong consistency when we are not careful. To this point, I want to introduce ConSysT. ConSysT is our object-oriented language, which tackles the problems of consistency and availability. ConSysT is an extension to Java, and it has support for replicated objects. In ConSysT, every replicated object can have its own consistency level, thus allowing you to program with multiple consistency levels in the same application. A type system then ensures that you are only mixing the consistency levels of different objects correctly. In the next slides, I want to show you how ConSysT looks like and how this type system ensures consistency. Let me start by introducing the object-oriented design of ConSysT. Here we see a standard Java class of a concert for a ticketing application. A concert has a date, it has a concert hall where it takes place, it has a band, and it has a counter that counts how many tickets are already sold for this concert. Then it further has two methods. One method returns the number of sold tickets by just getting the value of the counter. And the other method is for buying tickets. We can now use ConSysT support for replication to distribute this application. On the right side, we see the code for that. The fields hall, band, and sold tickets are now replicated object, as indicated by the type ref. A ref is a reference to a replicated object, which is used by the programmer to perform operations on the replicated object. For example, accessing fields or performing methods. The consistency level of the replicated object is also seen in the type. For example, hall has the consistency level eventual, as indicated by the annotation @EV. The sold tickets counter, on the other hand, is sequentially consistent. In the method getSoldTickets, we see how we can access the field of a replicated object. Accesses to replicated objects always use the definition ref on references. So for example, to access the field value on sold tickets, we use soldtickets.ref.value. This makes accesses to replicated data explicit and signalizes to the programmer that remote communication can happen at that place. In ConSysT, we can have multiple consistency levels. Currently, ConSysT supports sequential, causal, and eventual consistency. We can see that we can order these consistency levels in a lattice, where at the bottom there are high available levels such as eventual consistency, and at the top there are strong consistent levels such as strong sequential consistency. Programmers can plug their own consistency levels into ConSysT and can use them. The type system will use this lattice to type check the program. I have now talked quite a bit about mixing consistencies. Let me show you now at an example what it actually means when we mix consistency levels incorrectly. Here again we have our concert example. We have a hall and we have the sold tickets counter. Also we have the buy ticket method. The buy ticket method increases the sold tickets counter if the hall has still seats available. That means if the number of sold tickets is lower than the number of seats in the hall, then we can still sell a ticket. Now, let's see what can happen when we have a program execution. So here we have two replicas. On the left side, we have the state for replica 1, and on the right side, we have the state for replica 2. At the start, in both replicas, the seats of the hall are 300, and both replicas have sold 200 tickets. Now, what happens when we on one replica, we decrease the number of seats by 100 and then try to buy a ticket. On this replica, the number of seats will now be 200, and when we try to buy a ticket, we can't do it because there are no more seats available in the hall. However, the hall is eventually consistent, which means that updating the number of seats may not be immediately communicated to the other replicas, leading to temporary inconsistencies. So replica 2 can still think that the number of seats in the hall is 300. Now when we try to buy a ticket on the second replica, we can do that because we still have seats available. So even though the sold tickets counter is sequentially consistent, we cannot buy a ticket on the replica 1, whereas we can buy a ticket on replica 2, even though we buy the ticket on replica 2 later in time. This is some behavior that we don't want to happen. So now, when we wait to propagate the changes, what happens is that on both replicas, the number of seats is set to 200, but the number of sold tickets is now 201, which is a behavior that we don't want to have. So what was the problem here? The fundamental problem is that strong consistent operations depend on weak consistent data. Here we see the code for the buy ticket method. In the first line of the method, we check whether the number of available seats in the hall is larger than the number of sold tickets. If that is the case, then we can sell a ticket by increasing the counter and returning the ticket. The counter is sequentially consistent and used at all places that are marked red. The hall is eventually consistent and used at all places that are marked green. We see that increasing the counter has an implicit dependency on the number of seats in the if condition. This flow from weak consistent to strong consistent data is disallowed and leads to the problems with consistency guarantees that we saw on the previous slide. Our type system will find such dependencies and disallow them. ConSysT only allows safe flows. We also have a formalization of our system. In ConSysT, we want to model concurrency and replication as replicas concurrently issue operations on replicated objects. We also want to be parametric on consistency levels, as there are multiple consistency levels that we can choose from. So what we did is we modeled a replicated store and multiple processes that access this replicated store. We proved type safety for our language as well as non-interference for consistency levels. I won't go into detail here for the formalization. You can find more of that in our paper. We evaluate our approach on 5 case studies. For example, the ticket shop case study that we saw here, as well as the message groups and a Twitter clone from papers in literature. We implemented the case studies in 3 different configurations. In the all sequential configurations, all replicated objects are sequential. In all weak, all replicated objects are eventually consistent. This is expected to be the fastest configuration, but sometimes applications and invariants may not be satisfied. Then we have the mixed configuration, which uses weak consistent objects only to the point where application invariants are always satisfied. We did our measurements on 3 different setups, on a local machine located in a single data center and geo-replicated over multiple data centers. We measured latency of performing an operation. The plots show the latency of the configuration all weak and mixed relatively to the latency of the all sequential configuration. Each bar color stands for one of the setups, local, data center, or geo-replicated. So for example, in the message groups case study in the data center setup and the mixed configuration, the latency of an operation is only 40% as long as in the all sequential configuration. What we see is that the mixed and all weak configurations both have a speed up compared to the all sequential configuration. We also see that, as expected, the all weak configuration has the lowest latency because here we can sacrifice application invariants. The speed up of mixed compared to all weak differs per case study. This is because the percentage of objects that can be eventual in the mixed case study is different per case study. So here we show the percentage of sequential objects in the mixed configuration. So for example, in the message groups case study, 33% of the replicated objects are sequential. We see that the amount of sequential objects directly influences the speed up that is gained by the mixed configuration. We looked closer at that effect and tested the message groups case study with a different amount of weak consistent objects. The y-axis again is the relative latency compared to all sequential, whereas the x-axis shows the percentage of weak consistent objects. We see that weakening the consistency level even in only a part of the replicated objects increases the performance. This increases linear. So as a takeaway, we see that mixed consistency gradually improves performance. So in this talk, I showed you ConSysT, language and middleware for programming with multiple consistency levels. It has a type system to ensure the safe mixing of consistency levels, and it uses object-oriented abstractions for that. You can find more of ConSysT in our paper, Rethinking Safe Consistency in Distributed Object-Oriented Programming, or on our website. Thank you for listening.